Hello there and welcome back to the Redstone Development Foundation server. In this video I'm going to be showing you a little, well, quite big project that I was working on over the last summer holidays, and which I left but then came back to and recently finished. And that project is my new 8-bit Minecraft computer. Let's just tell the guys that I'm recording. Oops, caps lock. Anyway, so yeah, let's do some overview of the computer specs. It has an ALU which computes all the arithmetic inside the computer. That takes about 7 ticks to do any operation. Once the operation has completed, the output can then be stored in any of the 7 dual-purpose registers. Well, not dual-purpose, multi-purpose registers. General-purpose registers, that's what it's called. So yeah, there's 7 general-purpose registers which can be accessed at any time by the CPU, and the CPU loop consists of pretty much just the ALU and the registers. The registers are just dual read RAM, which is designed by myself, and it's pretty quick and not too compact. Well, it was considered pretty quick and not too compact when I built it about 3 months ago, but now it's maybe a tad out of date. So yeah, now that I've done the ALU and the registers, I will move on to something else. Okay, yeah. The next specification I could talk about is the external memory, because since having only 7 different locations to store data, and that's not a terribly large amount, I decided to add on 31 bytes I think, maybe 32 bytes, can't remember, 31 bytes I think of external memory. And this is just single read, it's a dual read memory. Not designed by myself, designed by Zeomorpher, I think. Well, he compacted it, and it uses quite a nice mechanism, to be accessed by the CPU. The CPU has one more register apart from the dual registers, and that is called the address register. And it does what you expect it to do. It holds an address of the external memory. So say you were just computing something like 5 add 5, and you wanted to save it into address, I don't know, address 18 in external memory. First of all, you'd compute something which would create an answer of 18, and then you'd set the address register to 18. After that, you would compute the what did I say? Was it 2 plus 3 equals 5 or something? You'd compute whatever arithmetic or logic you wanted to do, and tell the using the instruction, tell the computer to save to the address which is stored in the A register. So that would then the address would then get exported down here and round there into the addressing of the memory, and your data will be saved. And likewise, to read from a location in memory, you first set the A register to the address you want using the ALU output, and then you use the read command in your instruction. That data is then read back into the CPU, which then can be stored into a general purpose register for later use, or for use, and that can all be done in 2 instructions. So it's pretty quick. That's pretty much it for the external memory. Now we can move on to the branching, conditional branching. Something which any good computer should have now in Minecraft is conditional branching. So when computing an answer, if an answer is true, no, well, if an answer is um, true to a condition or false to a condition, you can tell a computer to do different things. And the way I have this is having three go-to conditions. If the output is equal to 0, if the output is greater than 0, if the output is less than 0. This is done by a comparator here. Not comparator, well, yeah, kind of comparator. Yeah, kind of comparator here. And so when you'd want a condition, you could do the condition by using an instruction of the ALU, and then the output can then be checked using this purple logic here. If the condition is true, the address located in the A register will be used to jump the program counter to that address in the what do you call it, the program memory. That sounds pretty complicated, but it's actually not too bad. So say you wanted if the answer is 1 is greater than 0, jump to line 10. So what you'd do is you'd save 10 into the address register, do whatever arithmetic or logic computed your answer, and then using the instruction you'd check if that answer was greater than 1. If it is, the address stored in the A register would then be loaded into the program counter, which is here, and that would then jump to line 10 of the program memory. If it was false, nothing would be loaded from the A register, and it would continue cycling as usual. So that's pretty much the go-to condition, which again uses the A register. So the A register is pretty vital in this computer for the external memory and for the conditional branching. Next, what should I say? Next I'll talk about the documentation and the user input. User input was a little bit more complicated in this computer than originally expected, and there are two ways to input numbers. The first is the basic way of doing it, which is simply to set a number whichever you wanted. So 7. Choose a general purpose register by using this addressing system. So like 1, 2, or you could combine them to make 3, 4, 5, 6, 7, because there's 7 registers. And then so at the moment I've got 7. I'll write that to address register to general purpose register 3. So 2 and 1, and then just click write. That has then saved that number into the third register, which is this one here. This is the third register, and if you look down here, if you don't know how RAM works in Minecraft, you probably won't know what's going on, but these first three bits have been retracted on the pistons, and over here the rest of the pistons are still extended, indicating that the 7 was correctly saved to this register. So yeah, that's one way of user input. Another way is again using the using A register. This is also quite clever. I have the control logic set up so so if you set the A register to 32 and read from that address, obviously there are only 31 bytes of external memory, so it will try and access that. Nothing will be read because there are only 31, not 32. But instead, the user input will be read, and that can then be saved in the same instruction to or clock cycle to a general purpose register. So that's the second way of doing it, and that uses this grey wire here to access it, and then a bit of logic up here when reading, no, when using user input, these pistons will cut off the ALU output, so no output from the ALU will be feeding back into the registers, and then that means the user input can be written correctly to the registers. One of the final things I can talk about is the program memory, or the ROM. It's the same thing really. Basically this is where you load your instructions or write your code. ROM is read-only memory, so nothing can be written to here. It can only be read from it. And the way you write your code is that each of these lines here, each of these lines going across, go to a different command in the computer, and each of them is a different instruction bit. I'll talk about that in a minute. And so placing a torch here will do something different to placing a torch here. So placing different torches will effectively power different commands and different functions inside the CPU and computer. Hello. And since there are lots and lots of different lines in which you can place torches, you can do lots and lots of different instructions. So that's basically how the program memory works. Oh yeah, and the way that it accesses each different line of code, each different line of program memory, is that a program counter, which is here, which basically just counts up in binary. So this thing here counts up in binary, thanks to Hans Lemerson for this program counter, although I didn't explicitly ask you, I just hoped that you'd be okay with it. So if you do see this, sorry for asking, but yeah, thanks for this program counter which I used. It's a very nice design. This counts up in binary. The output is then loaded into a binary to decimal decoder, and using that logic, every clock cycle the binary number will be increased by one, so the decimal number will then be increased by 1, causing this to like jump on every clock cycle. The clock cycle I'm talking about is here. This is the master clock. I'll just turn this on and give you a quick demonstration. It's not set to any specific timing at the moment. It could be a lot quicker than this. But yeah, so every clock cycle this will change. So at the moment it's 2, now 3, 4, 5. If you didn't realise, this is binary, so 1 0 1 0 0, 0 1 1 0 0, which is 6, 7, and then 8. I'll just go and show this working with a binary decimal decoder. So 8 is being decoded, now 9 is being decoded, so this line will be powered off, then this line, and this line, and so on and so on and so on. And as you can see, the instructions are all the same here, because I was actually running the Fibonacci sequence, failing to run the Fibonacci sequence due to some errors and some bugs which are in this computer, which I'll talk about a bit later. But yeah, all these torches are different to run the Fibonacci sequence correctly. If you have seen my how to build a computer series, you'll know that the Fibonacci sequence isn't that difficult to do. So if I do release a world download, I challenge anyone to get the Fibonacci sequence to work on this computer. The clock is now turned off, but I just need to reset the program counter. To do this, this line here can be activated, and that resets the program counter. Another nifty thing about the program counter is that for the conditional branching, you want different addresses to be loaded into here, so different addresses can be decoded. So this bus here, from down there where my cursor's pointing, is run all the way up here, across here, and then loaded into this side. And if the condition is true from the go-to, this line will be powered. So about interruption. What was I saying? Oh yeah, I think Oh yeah, so if the condition is true, this line will be powered, causing causing the address from here to be able to pass through. So these will turn off, allowing the address to be passed through up here. That will then be be passed into these repeaters, and then since it will be true, this line, which is connected to the line down there, this line will be powered. These pistons push down, effectively, so then the power will pass through the repeaters into these Bezier flops, and then which is basically a memory cell, and then that will be loaded into memory, and the program counter will continue cycling from that address. So that's basically how that works. I would like to give you a demonstration of the computer running, and before 1.4 came out and the piston times were changed, I would have been able to, but the piston changing the piston timings have caused the ALU to screw up and drop blocks and cause double heads to be created, which is really annoying. Which means it's really buggy. Well, it's not really buggy. It's just occasional bugs mean that it doesn't run perfectly, and I'm pretty frustrated with that because I spent ages building this only to have it ruined by a Minecraft update. But there's nothing I could do about that really. I did spend a while debugging the RAM. That took ages to do, but that's fully debugged now, so I know my RAM works. These decoders, these can double heads can be created on these pistons due to the new timings and such. So yeah, it's a bit frustrating, but not much I can do about it. What else can I talk? Oh yeah, I'm going to explain the instructions now. This is probably the last thing. So I've talked about pretty much each individual component of the computer. Whether or not you understand it is another matter, but hopefully you understand quite a bit of it, especially if you have seen my How to Build a Computer series. So yeah, this is well, one instruction is made up of many different little, like, I don't know, it's hard to describe. Like one line of code is made up of different commands, different things the computer can do, but basically it is made up of reading from one register, reading from another register, doing something using the ALU, so adding, subtracting, or any logic function, dividing by 2, shifting, whatever. So yeah, so reading from one register, reading from another register, performing some arithmetic or logic on it, and then writing that back into memory. So that's the basic loop of the CPU. And obviously other things can be done, like you can read or write stuff to external RAM, and you can do different conditions on this. So it's not a terribly complex instruction set. It's pretty concise. It was initially optimized for speed, but I kind of dropped that idea. It's pretty quick, but not the quickest. So yeah, so this is the first register address to read from. Sorry, the second. I just decided to do 2 then 1 for some reason, not sure why, but yeah. So this is the address for the second register. This is the address from the first register. This is the address you want the ALU output to be written to. These individually, so these like 3 combine to make an address, but these are actually individual. So this updates the A register, so effectively refreshes or saves the A register, so saves whatever the ALU output is to the A register. And then if you want to write or read from RAM, obviously you can't do them at the same time. You would use either of those bits. And then this is for the condition. So if x equals 0, do something, x is greater than 0, do something, x is less than 0, do something. X is just an algebraic letter I gave to the ALU output. I could have called that anything. That's not really relevant. And this is the code for the ALU operation. I'll now go and explain the codes. So this is the documentation of the computer, and here are the ALU operations. So the first, this is like reverse binary. Normally we read from right to left, but I did it from left to right because that's how it's located on the ROM. So the first is OR. So it starts with the logic operations. So OR, NOR, AND, NAND, XOR, XNOR, and then A plus B, which is just basic addition, A being the first input and B being the second input. So A plus B, A minus B, which is basic subtraction, and then B minus A, which is the inverted subtraction. So it does, instead of like 8 minus 5, it do 5 minus 8. 0101, which is the 10th operation, I think, is divide by 2, and divide by 2 is achieved by shifting the bits. If you didn't know that, that's I think that's right shift. Shifting the bits right, is that? I can't remember which. It depends which way you look at it, but I think in this computer it's a right shifter. It's been that long since I built it. Yeah, but basically this is the shifter on the end. Did I label this? Shift right, yeah, I thought it was shift right. So yeah, this takes the output coming out of the main ALU and shifts it right. So that's what that does. That effectively divides the number by 2. And then the last two are used if you want to set all the bits to 0, which would be handy if you wanted to zero out a register, so clear a register. That's what you could use. You could just use the operation to do that, and if for some reason you wanted to set them all to 1, you could do that with the last instruction. That's a bit of a useless instruction, but yeah. The instruction layout goes as follows. So BBB, which is the read B address, AAA, which is the read A address, WWW, which is the write address, MMM, which are the memory functions, the green ones, GGG, which are the go-to conditions, and XXXX, which is the ALU operation. The rest of this on here, this just describes what I've already talked about, different colour codes for that, and this long line of text, this line of text. This is for the specifications, and this is for reading and writing to external memory, which requires a little bit more description. So yeah, I think I have just about talked you all into boredom and described pretty much every part of this CPU. Now that this is complete, I can't be bothered debugging it anymore. Just take too long, and I don't even know if it's impossible to. But I'm going to build a new ALU and then start work on a dual core computer or a Minecraft multiplayer. The multiplayer would be a lot easier, so I'm tempted to do that, but the dual core might get my reputation boosted further on this server, as I am an engineer at the moment and would like to be promoted. Sad, I know, but still something worth building for. So yeah, if you have enjoyed this video and would like to see more redstone videos or more of my contraptions that I've built on the RDF, please drop a like. So yeah, thanks for watching. Please like, comment and subscribe.